Hi everyone, welcome to another STEM tutorial. Today we'll be looking at the least squares approximation, in particular linear regression. So let's get started. So as you may have heard, the goal of linear regression is to find the best straight line through a set of data points. So here what we've done is we've plotted various experimental data points on an XY axis. And what we want to do is we want to figure out where does a line need to be to best describe the data we see here. Of course, one way to do it would be to eyeball it. So we could assume that we just kind of draw the line here through the middle. So I have the feeling the line would look best here. But the question really is, why do we want the line here? Why don't we put the line up here or down here? Well, we know here it looks like the optimal, but using linear regression, we can find the equation of our line, so our slope and y-intercept, mathematically. So for now, what I'll just do is I'll refer to this line that we drew here as our best fit. So we'll assume that we completed this linear regression calculation, and this is our best linear fit, where we'll refer to the y points as y, I, lin. And we'll use this line to help explain the concept of linear regression. So the goal of linear regression is to minimize the area between the y values of our experimental data points and our line of best fit. So what we're doing is we're measuring out what is the distance between this experimental data point and our line, and then we're squaring it. So you can imagine just drawing a square here. And what we're trying to do is we're trying to minimize this area. So here for this bottom point, x2, we have this distance here between our dot, our experimental data point, and our line of best fit, and we're trying to minimize the square of this distance, so the area. Here you can imagine having a bigger square then, something really big. So if we write this down mathematically, the way we can consider it is that we want to minimize the error of the following, and we'll go through it together slowly so that you understand. We want to minimize the sum of all of these squares that we've seen here. So I'm just going to note this by e subscript I squared, referring to the error of each square. So each square is represented by the subscript I, and we have 1 to n squares. And so how do we calculate this error? Well, we can define this error as what I've shown you, our yi experimental. So essentially the y values here of these different data points minus each of the y values of our linear fit. So like I said, this experimental value minus the y value corresponding to our line of best fit, and we square it so that we're looking at the area. So I write the squared up here. So if we extend this y linear here, we know that the equation of our line can be written as, we'll say our intercept, a naught, plus our slope, a1, times x. This is the same form as y equals mx plus b, but here we're just changing the name of these coefficients that we're trying to find out, are a0 and a1. So really we're trying to find out what are these coefficients so that we have the optimal line describing these different data points. So now when we know this equation here of our line, we're going to substitute it down in here. So if I just substitute this in here, we get that our sum of I equals 1 to n. So we're going to take the difference between each of our y's of the experimental points, and we're going to subtract this a naught minus a1x. We're going to square it. So again, we just substituted this into here to get this equation. Up until now, if you want to see what have we done, we're writing down this equation here and we're summing all of these areas here. So now I'll move on to show you how do we derive the equations we're going to use to calculate this straight line. So what I've done here now is I've just copied the equation that we discussed on the previous slide here. And I'm going to name the sum of our errors the variable s subscript r. And so now, as you know, what we want to do is we want to find these coefficients a0 and a1 to best optimize our linear regression line. And so to determine our line of best fit, what we need to do is we need to take the derivative of our sum of errors with respect to each coefficient. So with respect to a0 and with respect to a1. And we need to set this equal to 0. And so you may be asking yourself again, why do I need to take the derivative and set it to 0? So I'll just draw a brief plot to help explain why we need to do this. So here I'll plot the sum of our residual errors versus our y-intercept, our a0. So we're pretending the red line is going to give us our best linear fit and therefore our lowest sum of errors. So on this plot, I'm going to draw the red dot down here. And so now if we draw a purple line up here, for instance, first of all, we're going to have a higher y-intercept here. So we're going to have a higher a0 value. And as you can imagine, if we draw squares from some of these points, so if you consider we're drawing squares here, okay, that looks a bit more like a rectangle, but we're drawing squares here everywhere. We're going to have huge sums of errors. The error is, of course, 0 here when comparing this point to this line, but we have huge offsets here, so this is definitely not going to be an optimum. And so if we consider this purple line on the graph, we're going to have a very high sum of error. And the same goes for drawing a line that's closer to these points down here. Let's pretend it goes through an intercept of 0, but we would know with the same concept as the purple line that we have a huge sum of error. And so if we look at our sums of errors, it looks like a polynomial shape here. What we're doing is we want to find the minimum. And as you can recall from your calculus class, to find the minimum, you need to take this derivative here with respect to each of the coefficients and set it equal to 0. So this is just a brief explanation on why we're doing this. And so when we take the derivative with respect to each of the coefficients, the solution we get is equal to, and so you'll see here we have two equations and two unknowns. So we can solve for a0 and a1 coefficients. And I won't go through all the mathematical steps here. It's likely as well for a numerical course that you don't have to do these steps. It's really at the moment just to help you understand what is the concept, what are we doing, why is this value up here squared. So now I'll just write down the equations that you'll get when you rearrange, and we can use it in a simple example together. And just because I'm running out of room, I've copied the two equations we wrote down here and have reminded us that we're doing two equations and two unknowns. And so if you do want to try to rearrange this all, keep in mind that the sum of our a0 can be described as a value n, so our number of data points, times our coefficient. Anyway, so when you rearrange this, what you'll get is that your coefficient a1 will equal your number of points, n, times the sum of your xi times yi values minus the sum of your xi sum of your yi values divided by your total number of data points sum of xi squared minus, and here we take the sum of xi first and then we square the whole thing. So here we're taking each xi, squaring it and then adding it, and here we take the sum of each xi and then we square it. And then our coefficient a0 that we need to find will equal the mean of all our y values minus the a1 value that we just calculated up here, which we'll do in a moment with an example, times the mean of our x values. So I'll just remind us that these are the means down here, mean of y and mean of x. So now where we've been introduced to these lovely equations here, let's apply them in an example. So here I've again written down these two equations that we've derived, and we'll use them for this example here. I've put together only 3 data points, so it's easy for us to calculate together. And we're going to use linear regression to fit to this data here. And so what I would recommend is the first thing we're going to do is calculate each of these terms and then substitute them into this equation here. So the first thing we want to define in our A1 equation is n. So this is again our number of data points. Here we can calculate, we have 1, 2, 3 data points. So our n is going to equal 3. The next term we're going to calculate is our sum of xi, yi. So let's just write out the steps together so that we all know what we're doing. The sum of our xi, yi equals 1 times 2. So again, our y times x value. And then we add 2 times 4. And then we add 4 times 6. And if you calculate this, you'll get an answer of 34. Let's move on to the next term. So as the next step, we're going to sum our xi and then sum our yi and multiply it together. So here, the sum of our xi is 1 plus 2 plus 4. So I'll just write down 1 plus 2 plus 4, since we're writing out all the steps here. And then we'll sum all our y values, which is 2 plus 4 plus 6. And so when we calculate this, we get an answer of 84. As a next step, we're going to calculate the sum of our xi squared. So here the sum of our xi squared will equal 1 squared plus 2 squared plus 4 squared. You get an answer of 21. And then doing the sum of xi and squaring the whole thing, so looking at this term here, then we get 1 plus 2 plus 4, and then we square the whole thing, and we get an answer of 49. So with this, we have all the terms we need to substitute them in this equation here and calculate our A1. So let's do it together. We see that our A1 will equal our n, which is equal to 3, times the sum of xi, yi, which is 34, minus the sum of our xi, yi, which is 84. So we've calculated our numerator. If we look at our denominator, we have again our n, which equals 3 times 21. So the sum of our xi squared minus 49. And so when we calculate this, I'll write it down as a fraction value since it'll make our intercept nicer. We get an answer of 18 over 14, which equals 9 over 7. So with this, we have our answer for A1. Our A1 equals 9 over 7. So now all we have to do is go back and calculate our A0 here. And recall for our A0, we need to calculate the mean of our y values and the mean of our x values. So let's do that together. We'll write it up here. So we know the mean of our x values will equal 1 plus 2 plus 4 over 3, which will equal a value of 7 over 3. So you see, we're going to keep it as a fraction, since you'll see shortly that the values are going to cancel. We're going to get a nice round number. And then if we calculate the mean of our y value, it will equal 2 plus 4 plus 6 all over 3. And we'll get an answer of 4. And so substituting it to get our A0, so our intercept value, we get A0 equals 4 minus our A1, which is 9 over 7, times our mean of the x value, which is 7 over 3. So our 7's cancel nicely, and we get our A0 equals 4 minus 3 which equals 1. So with this, we solved for our y-intercept value. And so we can write down our equation of the line. So we know we've said our y equals our a1x plus a0, or our mx plus b, whatever you want to call it. And so we get an answer that our optimal equation of the line to fit to these data points will equal y equals 9 over 7x plus 1. And with this, we've answered the question. So hopefully by now you have a better understanding of linear regression. We have 2 further tutorials that may be of interest to you. In one tutorial, we'll be covering the r-squared value, or the fancy mathematical term, the coefficient of determination. If you're not interested in the r-squared value, but you'd like to continue practicing linear regression problems, we recommend you check out our linear regression exercise tutorial. So here we'll go through a couple linear regression problems together in various forms that you could encounter linear regression in real life or on a test. If you enjoyed this tutorial, please give us a thumbs up and hit subscribe to get more numerical methods tutorials. Thanks for watching.